Hi, everybody, and welcome to the October edition of Astronomy on Tap Groningen. I'm Nika, one of the organizers of the Astronomy on Tap, and tonight, together with Jake, I will be your host. First off, I would like to start with mentioning that this week we are celebrating World Space Week. What this means is that we celebrate science and technologies and their impact on the overall human well-being. So today, it's actually a great way to start the celebration, to join the Astronomy on Tap Groningen. And how we are structured is as usual. So as our every online event, but in case this is your first time being with us, first off, we have two speakers. And these two speakers will give talks for approximately 20 minutes. During their talks, we encourage you to ask questions. So either ask them in the comment of this video, ask them on social media, send us a private message, however you like. We'll find it, and then after each talk, I will redirect your questions directly to the speakers. Then, after these two speakers are done, we will have a short break in order to prepare for the pub quiz. In this pub quiz, we will have two rounds. So first round is reserved for the talks that we will listen to tonight, so listen carefully. Second round is random general astronomy round. So yeah, prepare your beers and listen carefully what we have prepared for you tonight. So first off, we have Anne Hutter. Anne Hutter is a postdoc here at the Kaptein Astronomical Institute in Groningen. And she did her PhD in Potsdam, after which she moved to Australia, where she did her first postdoc in Melbourne. Now she's here with us, and she's studying first billion of years of the universe. So she will talk to us today about traveling back in time to the first galaxies. Here you go, Anne.
Thank you. All right, sorry for the slight delay. Thank you, Nika, very much. I'm going to tell you today about I want to take you on a journey back to the very first galaxies in our universe. And as all journeys, we start here in Groningen. And as you can see, you probably know this kind of scenery in Groningen. And unfortunately, also the weather in the Netherlands is not necessarily always that great that you can see your final destination from here, where we want to travel tonight. So mostly it will be cloudy. I assume also tonight, if I look out of the window, it's really cloudy. So yeah, Groningen is maybe not the best spot to spot your final destination today, the first galaxies where we want to travel to. But some other places on the Earth are actually really great, where you can see an awesome sky. So here's, for instance, like if you're in Australia, you will see a lot of stars. You can see here like the Milky Way, see here across the sky. So what I want to do with you tonight is travel to the first galaxies. And for now, we will travel basically, let's imagine like on a photon, so a light particle. And we travel at the speed of light. So first, we have to travel out of Earth. And so from Earth to the sun, if we travel at the speed of light, it would take us 8 minutes. But our destination is not the sun. The sun will come later, I believe. We will travel out of the solar system. So from Earth, we will pass Mars, Jupiter, Saturn, and it will take us a couple of hours to travel at the speed of light out of the solar system. So roughly 6-7 hours, then you're out. And if you travel then another 1,000 years or more than thousand years ahead, then we will see our own galaxy from the top. So this is what you see here on the right hand. That's a sketch of the Milky Way. You can see here the position of the sun where all the orange lines meet. You see the center of our galaxy. And then you can see also like how far our sun is, for instance, away from the center of the Milky Way. So this is like 26,000 years, light years. And our whole galaxy is across roughly 100,000 light years wide diameter. So if you want to travel from one end to the other on a light particle at the speed of light, it will take you 100,000 years. Okay, so now we are looking at the Milky Way sort of, you might imagine, could say like from the top. So now we turn a little bit around, we move around, so we can see the Milky Way from the other direction. So you can imagine we are moving by 90 degrees downwards. And then what you actually see will be this. We'll see mostly a disk. So what is here sort of these spiral arms and sort of this round shape, we'll see here a disk. You still have here the galactic center in the middle, same as we see here. And then also around, there is what we call the dark matter halo. So as you notice, you don't see any light from there. So most of the light will come from the disk. So this brings us to the question, like, from what does a galaxy actually consist of? What is it made of? And obviously, we can zoom in. Let's zoom in into the Milky Way, zoom into one of the neighbor regions. So this is actually a nebula. And then we maybe can ask this question, what does a galaxy consist of, or what is it made of? So the obvious content is obviously, as you can see already from these pictures, is stars. Stars are emitting light, and so this is obviously what we're seeing. So that's really easy. But it also consists of gas. So the most majority of this gas is hydrogen and a bit of helium. And then there are traces of carbon, oxygen, nitrogen. But mostly we astronomers don't like it to be complicated. So we make things really simple. So for us, it's basically hydrogen, helium, and metals. Everything which is like heavier than helium is, of course, metals. All right, so this is what a galaxy consists of. So, but if you look at this picture, we already can see like we have very bright stars, we have like larger stars, we have smaller, fainter stars. And the question comes like, why is that like this? Why do we see different types of stars? So therefore we can think about like how does it actually this whole circle works? So stars actually form from the gas in the galaxy. So you will have a gas cloud, and because there is gravitational forces, this gas cloud will collapse, and from this collapsing gas cloud, stars will form. Actually, when it's this gas cloud will also sort of fragment into smaller different pieces, so you will form more massive and less massive stars. And the most massive stars, they will actually, they die a very spectacular death, you could say. They basically explode. And before they explode, they actually produce all these, what we astronomers call metals. So for instance, carbon, oxygen, and if we're really heavy, nitrogen. And this explosion, because they explode, then they inject these metals into the rest of the surrounding, in the environment, so the gas. And so this enriches the gas with metals. So suddenly your gas, if it initially just consisted out of hydrogen, helium, also has now metals in there. So now you can imagine the next generation of stars will form from a different type of gas. This gas won't only have hydrogen, heliums, but it will also have metals. So why is this crucial? Why do we care about this? Because this actually plays a role when we look at like the history, when we will travel back in time. we will see how basically the type of stars we are seeing are changing. So what are we expecting to see? So how do the stars change? So very early on, you can imagine in the universe, there was just hydrogen and helium. You had basically no metals. So in these times, very massive stars formed. They're very, very massive. And because they're so massive, they use their energy very, very quickly. So they have a really short life. They don't live long. They're massive, but they live very shortly. Then they explode. And as you learned, they eject the metals into their surrounding, in the surrounding gas. And so the next stars that are forming, they have some metals. And now you can imagine if you have this gas cloud, basically what the metals can do, they can cool this gas cloud a little bit. And this turns out that those stars are slightly smaller and they live a little bit longer. So again, and from those, the most massive ones are exploding and they enrich the gas more and more with metals. And then the third generation of stars, which also our sun is part of, they actually contain like even more metals, and they live an even longer life, and they're less and less massive. So now we already can see the more metals we have in our gas, the longer is the lifetime of a star. And if we are traveling now back in time, we basically go the opposite way around. We will go from the long living metal-rich stars to the metal-poor, short-lived stars. All right. So let's board and let's go to our trip to 13.4 billion years ago. So wait, but first we need to check how can we travel actually back in time? Because we don't have a time machine, right? So how we do this is actually pretty cool. So imagine you have a candle and you all know like when you lit it, it will burn down. So after a minute, nearly nothing will have changed. After an hour, a little bit will have burned down. And after 2 hours, even more will have burned down. All right. So what does that happen if I put this candle now away? So if I put it like a light minute away, so that would be, I put it between the Earth and Venus. I put a candle there, I lit it at the same time. What would I see after a minute? Or if I put a candle basically on Jupiter, what would I see? And I could go even further to Saturn or Uranus and ask this question. So because it takes the light, this time to travel, basically from, in this case, from the middle between Earth and Venus to come to Earth, it takes a minute for the light to travel. We actually will see the candle, the image, right at the point in time when it was lit up. So similarly, if we have like an hour ago lit up, if an hour ago the candle was lit up, let's say on Jupiter here, we will exactly see the same thing. So now you can imagine this way, the further something is away, the further we go away, the more we look into the past. And this is exactly what we're doing, what we astronomers are doing. So here I'm showing you sort of a brief history of the universe, you could call it. So we are basically here today. Here you see our telescope. This is, for instance, the Hubble Space Telescope. And here's the Big Bang. And what we will do, we basically will look through here to the very first galaxies, which roughly formed 400 million years after the Big Bang. And yeah, that's roughly 13.4.3 billion years ago. All right. So if you take the Hubble telescope and we look at an image, what do we see? So this is, for instance, the Hubble Ultra Deep Field. So now you can see here like bigger galaxies, smaller and really, really tiny ones. So the bigger one and brighter ones, that probably will be the galaxies that are close to us, that we see very well. But if you want to check for the very first ones, you need to look like for the really, really tiny and faint points here on this map. Okay, so how does, if we travel now along, we go deeper and deeper into this image, how does, for instance, a galaxy like our Milky Way changes with time? So initially, if we travel 3 billion years into the past, we still see, yeah, it's a good sized galaxy. It still has sort of a shape like a disk. If you go further and further, what you can see, the galaxy becomes smaller, and yeah, it mostly becomes smaller, and also it will become less massive. So for instance, if we have the Milky Way and we go like, let's say 10 billion years into the past, it will only have a 30% of its current mass, what it has today. And also it will be only roughly 30% in its size. So we can go really to the far out, one of the furthest observed galaxies, which are shown here. So here again, you have the observation field. And in this image, you already can see like, you really have to zoom in to find one of the furthest away galaxies. This one is, I think, around 13 billion years away. And you really have to zoom in. And some are even here so tiny. I mean, if you look in the big picture, you won't see that galaxy. And the only reason that we actually can observe this is because we have sort of an augmentation glass in front of it. So there is a cosmological, or in the universe, if you have a really massive, for instance, galaxy or something in front of this very distant galaxy, it can basically act as an augmentation glass. So only because of this, we can sometimes actually observe these very first galaxies. And the current record holder with the most distant galaxy to date is this one. So this is 13.4 billion years ago, which is 32 billion light years away. So it would take, yeah, 13 billion light years. So this galaxy is 25 times smaller than our Milky Way. It's 100 times less massive, but it forms stars 20 times faster. So you can imagine those first galaxies, they were not as well behaved as our current Milky Way. They are far more violent. You have far more massive stars forming, exploding, pushing gas around. So it won't be well-ordered structures. There will be more massive. It's far more, you could say, like a violent environment at these times. So, but the problem is that these galaxies are really far away, and they're really hard to observe because, first of all, they're smaller in size, as we have seen, and they're fainter because they're further away, and they are smaller in size. So, for instance, here you can see this is another picture from the Hubble Space Telescope, and all the circles around here, there you actually see a very first galaxy. However, if you just look at the pictures, you hardly see something. So this is actually a really open research question, like when did actually the first galaxies form, at which exact time? We don't know that today. We only have some hints or some estimations. And there will be telescopes going up, which will even look deeper. For instance, like the James Webb Space Telescope. So stay tuned. So within the next years, it will be very exciting because more and more we will be able to look deeper and deeper into the universe and probably see much better some of these galaxies. So that is really exciting. However, there are other ways to do this. So we can actually learn more about these first galaxies. We don't necessarily need to directly observe this. And the question is how? So what can we observe otherwise than directly the galaxies? So imagine you have these galaxies in the early universe, But that's actually not everything that is there. So between the galaxies, you will have gas. And this gas consists of, if you go from the numbers, it's 90% hydrogen and 10% helium. So the entire universe is basically, let's say, floated by hydrogen gas and a bit of helium. And before these very first galaxies form, even there is light in the universe, the hydrogen gas is what we call neutral. So what you can imagine, if you have a hydrogen atom which consists out of a proton and an electron, they will be bounded. So the electron goes around maybe the proton, if you want to imagine it like this. But then these first galaxies appear. And what they bring into the universe is light. And light is energy. So now you can imagine you have these light particles emitting from these galaxies. And when they hit on a hydrogen atom, they can ionize it. So the electron will move away from the proton. They are not bounded anymore. And that's what we call ionized. So what happens then is like, if we have here, for instance, a galaxy and here another galaxy, the light that these galaxies emit will build up basically regions where this hydrogen is ionized, while around everything stays still neutral. So you could say that this light from the galaxies that they emit, they basically leave footprints in the what we could call the intergalactic hydrogen gas. So there are, let's say, these are the first two galaxies, but with time, more galaxies will appear. So you will find more of these ionized regions coming up. Also, the galaxies become more massive. They form more stars. You have seen as we travel back to the first galaxies, they become less and less massive. So if you are traveling back again towards today, they're becoming more and more massive again. So they produce more stars. The ionized regions become larger. And this continues until the universe is actually completely ionized. The gas between the galaxies is completely ionized. And that's roughly when the universe was 1 billion years old. So 12.7 billion years ago. So going slightly back again, so how does that help us? So the key thing is that we actually that this neutral hydrogen gas, so not where it's ionized, but where it's neutral, this emits a certain light, a radiation. The astronomers, so for us, it's a 21 centimeter radiation because this light has a wavelength of 21 centimeter. So the neutral hydrogen will emit this radiation. And now you can imagine we will get images at each point of time of the distribution of the neutral hydrogen around here. And these 21 centimeter light particles, photons, they will travel back to us to Earth. And this is where our journey basically ends. We will board one of those photons that emitted from the intergalactic hydrogen gas like 12.7 billion years ago, and we will travel back to Earth. And you should be careful, you probably might be hopefully lucky that you will be detected by LOFAR. So that's one of the radio telescopes that observe this kind of radiation and which aims at making these pictures of the intergalactic hydrogen gas. And as you can see, this is basically a picture how such LOFAR stations look like. So they consist out of many types of dipoles, and they're actually all across, as you can see, Europe. So in the Netherlands, actually not so far away from Groningen, is the main core. So there are many stations. In the Netherlands, probably there are most stations, but it goes as far as like the UK, Sweden, Italy, and so on. And this is very exciting because now you can imagine we can actually learn something about the galaxies from their footprints in the intergalactic hydrogen gas and by directly observing it. Thank you, and looking forward to your questions.
Thank you, Anne. I never know if my clapping is seen, but bravo, and thank you. This was actually a very nice talk for this World Space Week, because you mentioned both the technology and the science that we do here in the Netherlands a lot. But we got a lot of questions, so I will immediately redirect the questions to you.
Yeah.
So first off is the question, how old are the oldest stars that are still alive today? Are now only third generation stars alive?
As far as I know, we also observe population 2 stars. Well, they're probably now not alive anymore. We cannot observe them. It depends very much. So currently, we probably don't see population 3 stars. So the very first generation stars, we don't see them. The second population, I mean, if there are areas in the universe where there's not many metals in the gas, they will still form. So it's just a question, probably in our Milky Way, we won't see those, no. But I mean, yeah, it depends sort of where you are in the universe.
But so there is also a related question. So why the stars that existed first died so fast?
Because they have no metals. You basically and metals serve as coolants. So you can imagine the gas sort of, because you have metals, can better cool, and this cooling enables that you can form smaller stars. And the problem is they have your really massive stars. They basically, let's say, they waste their fuel very quickly, and this is why they basically have no fuel left, because they're so massive, and they basically use a lot of it, and then they just blow off, and there is no fuel. They are running out of fuel.
Yeah, that's there is one question that is related to the Hubble Deep Field image that you showed, which I think is always very interesting picture to show in this kind of talks. But there is a question that how do you distinguish actually between these faraway galaxies and them actually being something else? Because it's a very, as you said, it's a very tiny spot. It's not the ones that we actually can say this is a spiral galaxy, this is elliptical. Yep. So how can you distinguish between it being a galaxy or something else?
Yeah, there are basically 2 main approaches which people do, and that is what you observe is basically, I mean, you observe sort of the whole spectrum, so the light at a lot of different wavelengths. And the key thing is what you have to remember, these galaxies, they lie in a universe where the universe is still partially, so the gas between the galaxy is neutral. So you basically, what you will see, I don't know, if you imagine you have a light curve like this, at some stage you will have a cut, and then everything will be absorbed because you have neutral hydrogen there. And basically, if you have this strong cut, that's one of the indicators, if you see that. Or you have particular emission lines from hydrogen, for instance, where we know exactly the wavelength and we can observe it, and we know then, okay, that was this time. And those are basically the 2 ways. But it's a very hard business, and I mean, I'm not an expert in this, but how you observe them, but there are many challenges to it.
I don't know if I mentioned also at the beginning, when I introduced you, that you're doing a theoretical part and computational part of the astronomy. So maybe the question of observing is not the best one to ask, but in general, it's very hard, right? You cannot just look at them and say, okay, this is a galaxy, this is not a galaxy. So there are various ways to check this.
Yeah, and also to rule out that it's not something at lower redshift.
Yes. There's also a question, if we are looking back in time to stars and galaxies far, far away, does it mean that they might not exist anymore right now?
Yes.
Yeah, so this is a very straightforward one. Yes, of course. And there was one more question. So yeah, when you were showing the Milky Way traveling back in time,
yeah,
you were saying that galaxies, when you're traveling back in time, they're getting smaller and smaller. But was it really that they're getting smaller, or was it just the effect that you have because they're further away?
No, that is real. So they really be getting smaller. They are becoming less massive. You can imagine if you go the other way around from very early to now, basically what galaxies do, they start as like, let's say small galaxies. And then during time, they accrete basically the gas that sits between the galaxies that is accreted. And so then they grow. And yeah, obviously if we're traveling back in time, they're becoming smaller.
Yes, and you also know where they actually are, so you can actually say how big it is, even if it's further away, if you get it right, that it's far away. But okay, thank you, Anne. There are more questions, but if we didn't say your question, please join us in the pub, in the virtual pub that we have. And Anne will be there also during the pub quiz and after the pub quiz for the discussion. So thank you, Anne, once again. And the next speaker that we have is Francisco Tapia Vasquez, and he is a PhD student from the Institute of Radio Astronomy and Astrophysics in Mexico, and he is studying stellar atmospheres in solar-type stars. So therefore, today he will talk to us about Sun, our nearest star. Yes, so you can start, Francisco.
Thanks. Okay. Let me see. Okay. Okay. So thank you, Nika. Hi, everyone. My name is Francisco Tapia. I'm currently doing my PhD at the Institute of Radio Astronomy and Astrophysics at the National Autonomous University of Mexico. And my research is about modeling the chromospheres and solar-like stars using the light that can observe with radio telescopes. And that is what I will talking about today, the Sun or near stars. But before anything else, I want to thank the organizer of Astronomy Tab for having invited me. Well, I'm very happy to talk about a subject that I'm very passionate about with people from a beautiful city such as Groningen. I've been there 2 or 3 years ago, I don't know, but it's an amazing place. So, well, anyway, let's get started. The Sun, as we know, the Sun is the most studied astronomical object in the history of humanity since the very first human settlement. But clearly it's not by chance, since our life is possible thanks to the energy it provides us. The Egyptians, the Greeks, the Mayans, and now us have studied the Sun not only out of curiosity, but also because, for instance, it gives us information about what would be the fate of our planet. Now you may tell me, Francisco, if the Sun is the most studied astronomical object, we know everything about it by now, right? There is no point in continuing to study it. And the question is, sure, we know the Sun very well, but not really enough. There is still many questions that we must answer. Now you may wonder, what are those questions that no one has been able to answer about our near stars? Well, several questions are still found by the people study the Sun and the stars, but I would like to focus in 2 fundamental things that can give us some clues to solve other questions. These 2 things are the solar cycle and the coronal heating. So let's start with the solar cycle. You are probably wondering, solar cycle, what is that? And well, the solar cycle is derived from something like this. I don't know. Yeah, something like this. A spot on the visible surface of the sun. So we can think about the lunar cycle, where the part that is illuminated by the sun changes with the time. But in the case of the sun, this change is not evident if we don't have the help of some instruments. And you could say, what about these spots, these sunspots? Long history short, the sunspots are darker, cooler areas on the surface of the sun in a region called the photosphere. The surface of the sun, also called the photosphere, has a temperature around 6,000 Kelvin, while the sunspot has a temperature of about 4,000 degrees Kelvin. So they are much colder. Due to this, they look dark in comparison with the brighter and hotter region of the photosphere around them, like we can see in this image. Moreover, the sunspot also can be very large, up to 50,000 kilometers in diameter. They look quite small if you compare with the size of the sun, but actually they can be as large as the Earth, even larger sometimes. This means that the sunspots are too big for us, but too small if you compare with the whole sun. And these sunspots are generated due to interaction with the sun magnetic fields, which are not fully understood. And for that reason, nowadays, many people around the world are building big telescopes to better understand these spots. But the study of the sunspot is not new. Some records of observation made by ancient civilization have been found, but the formal study started with the invention of optical telescopes, like in this image, in the left image, which allowed us continue observation of this sunspot. And as we know, the sun has a very intensive brightness, and our eyes are not designed to observe it directly. So to study them, we have to project it in a white background, like this. And the result of this observation can be seen in the right image. They draw day after day the progress of this sunspot, and we can see that they move from the equator to the high latitudes. But of course, the scale of this sunspot doesn't correspond to the real scale. Well, after observing the sun for some years, we have learned that sometimes during the solar cycle, when the sun doesn't have any spot, there are a period of time that is called solar minimum. Like in this image, we can see that there are no any sunspot. And in other hand, there are a period of time when it has a lot of sunspots that are called the solar maximum, like in the right image. But if we are patient and constant enough with our observation, we can observe that this behavior is cyclical. This period where where there are many sunspots, and the period where there are a few are repeat approximately even 11 years. And this is what we call a solar cycle. In this plot, we can see in the x-axis, the time, and the y-axis, there is a number of sunspots recorded each month. Okay. As we can see, there are times when the solar maximum is intense, like in this cycle, in the 19th cycle. And other times that is so weak, like in the last cycle. And the same behaviors happen with the minimum, which sometimes is wider and sometimes is shorter. And nowadays, we have developed instruments that allow us to study this sunspot more in detail. And this image, the right image, where with the help of magnetogram, which is nothing more than an instrument that measures whether the polarity is positive or negative, we can see that sunspots have both components. And if we study the sun on a large scale, we can assume that the polarity is similar to that of a magnet. So over time, they change the polarity and that means in one cycle, it has a magnetic configuration, let's say positive and negative. And in the other cycle, the polarity will be negative, positive. So this behavior is known as Hale polarity law. In addition to the change in polarity and the amount of sunspot in each cycle, another phenomenon which appears when we observe for a long period of time is that the sunspot change in position in the solar disk. They don't always remain at the same latitude, and when the sun is at solar maximum, let's see, the solar maximum, the sunspot shift about 30 degrees south and north. And as we get closer to the solar minimum, this sunspot get closer to the sun equator. And as we can see in the video. Okay. Now, perhaps you remember that a while ago, I have mentioned the photosphere, which is a layer on the outer atmosphere of the sun. And let me say another couple of things about it, about the photosphere. We know that the other part of the sun is composed of the photosphere, which is the visible surface, and it has a temperature around 6,000 Kelvin. Above the photosphere, we have the chromosphere, which is a layer that goes from 4,000 to 10,000 Kelvin. And by the way, the existence of this layer is an unresolved question too, but I will tell you about in the next astronomy tab, if you invite me. And finally, we have a very special layer that is called the corona. The most surprising thing about the corona is that it has a temperature around 1 million kelvins, and we don't understand why this happens. This brings us to the next unresolved problem in solar astronomy. What is hitting the corona, and how can it reach such a high temperature? Well, the high temperature, the corona's high temperature are a bit of a mystery. Imagine that you are sitting next to the campfire. It's nice and warm, but when you walk away from the fire, you feel cooler. And this, in the sun's corona is the opposite. When you move away, you feel hotter and hotter. Okay, so the sun's corona is the othermost part of the sun atmosphere, and yet somehow is the hottest. The corona is usually hidden by the bright light of the sun's surface, which make it difficult to see without special instruments. However, the corona can be seen during the total eclipse when the moon passes in front between the Earth and the sun. And when this happens, the moon blocks out of bright lights of the sun, and the glowing white corona, like this, like, oh, I don't know. Sorry. Well, The glowing white corona can be then seen by surrounding the eclipse sun. And as we can see in this image, but I don't know why. Okay. The left image comes from a NASA mission called IRIS, whose main objective is provide one possible answer to these questions. The mission has discovered package of very hot material called heat bombs that travel from the interior of the sun into the corona. In the corona, the heat bombs explode and release the energy as heat. But this is not the only mechanism. There are many ways in which the corona is hidden. And in the early 60s, the advent of space exploration brought us confirmation of a remarkable prediction by the theoretical solar physics named Eugene Parker. And the corona is, the corona is composed mostly of plasma and ionized gas, but was not static. Instead, the solar plasma flowed outward from the sun, eventually reaching supersonic speed as fast as like around 800 kilometers per second and filling our solar system. Eugene Parker named it the solar wind, and we can see in this video we have the corona, and it extends through the solar system, and this is called, and these little things is called solar wind. And but the corona temperature causes these particles to move at very high speeds, and these speeds are so high that the particles can escape from the sun's gravity. Another phenomenon that connects sunspot and the corona is the coronal mass ejection, or CME. CME is a significant release of plasma and magnetic field from the solar corona, and this ejected material can escape from the sun during solar eruption, like solar flares and filament eruptions. But CME most often originate from active region of the sun, such as groups of sunspots associated with flares. And depending on the location of the eruption, the blast could either miss Earth, be partially or full Earth direct. And Earth direct CME will look like a partial or full halo in the image from SOHO, like in this video. So it explodes, and the particles reach us. When this happens, the CME will arrive at Earth after 24 hours or more, depending on the speed of the CME, and will likely cause a geomagnetic storm, and has the potential of display auroras in the poles, in the North and the South Pole. At this point, you may tell me, okay, great, Francisco, but why is the solar cycle and corona important? Well, first of all, sunspots add visual markers of the magnetic field that emerge from the solar interior. And these magnetic fields power solar flares and coronal mass ejection. If we understand the corona, we could know the conditions under which the solar flares form, and sometimes can generate solar mass ejection, which can affect us. So in this video, we can see the magnetic field emerge from the solar interior through the sunspot, here explode and expose material through the solar system, and this plasma can affect us. Okay, but how could solar activity can affect us? Well, this activity has a great impact today, since we are living in a highly technological society, and the main effects of this phenomena, such as CME, can manifest as an interruption in the navigation systems, like GPS, that could affect boats, planes, airplanes, and even our smartphones that we use every day. And also a loss in communication, and in some circumstances, partial loss of power supply. Therefore, a solar storm can generate billions of dollars in losses. And to prevent the impact of this type of phenomena, many countries, including the European Union, have created agencies that are monitoring all time this type of disturbance. And this type of disturbance is called space weather. And for this reason, ground-based telescopes and space missions have been developed in recent years with the main goal of observing and fully understanding solar activity. In 2018, I think, in 2018, the Parker Solar Proof space mission was launched with the main goal of bringing us closer and touching the sun for the first time. And this mission has been released to help us to solve the coronal heating and monitoring the solar corona. In the other hand, we have the ESA Solar Probe, whose main objective is to study the sun magnetic fields too close and help us to understand also the coronal heating. But to get a better understanding of the magnetic field that is responsible, as we know, as we see, for sunspot, a solar telescope has been built in Hawaii and is the Daniel Inouye Solar Telescope. Okay, in summary, we have seen that all we know about the sun is really not enough, and there is still a lot of work ahead to understand his behavior in the future. And to understand his behavior, and in the future, we can be able to protect ourselves from his activity. And I think there is this is all. And thank you so much for your attention. And if you want to know about my work, please feel free to visit my personal page, scan the QR. And well, I'm happy to answer the question you might have.
Thank you, Francisco. It was a very nice talk, and especially with all of these animations and videos that you showed. It's very interesting to see how actually we can make very nice videos of nearby things like our sun. But in your PhD, do you also study the sun, or you only study solar-like objects?
Both the sun and the stars, like the sun. So it's because it's so close. And okay, I study about
both, but you do directly observations of those. You do the observations.
Yes, with a radio telescope called ALMA.
Yes. Yeah, which is very good telescope.
Yeah.
So yeah, we also got a lot of questions again. So yeah, I will probably not be able to direct all of them. But first question is, in which stage are we now of the solar cycle? Are we in the minimum or the maximum?
Nice question. Now we are in the solar minimum, but in the next month, well, we are in the 25 cycle, but now we are in this month, we'll be in the 26 solar cycle. So we are in the minimum.
But entering a new one.
Yeah.
Yes, as we saw from this graph that you show, it's actually maximum.
Yes.
Yes,
we are here. I don't know. Okay. I don't know why. Okay. Well, we are at the end of the 24.
Yes.
And we are in the 25. We'll be in the 25.
And so there is one question that is related to this. So that says, I heard that in the 16th century or so, there was a long-term minimum in the number of sunspots. Is it known already what the reason was? And how stable is the solar cycle? Is it always exactly 11 years?
Good question. I have seen someone talk about mountain minimum, right? In some, here in Astronomy on Top. But I'm not the expert in this topic. But yes, in the 80th century, we had a unusual sunspot cycle, because there was not a sunspot, but we don't know why. Probably will be could be caused by solar observation. We don't know, but we have seen that solar cycle is around 11 years, but it's not exactly. No?
We can also see kind of from this graph bit, maybe by eye, that anyways, it's very much periodical.
Yes, it looks like a periodical thing, but
we'll see.
Yeah.
Okay, so we have also a question: what does the corona have to do with solar storms?
Because in the corona, the magnetic field's rich, and we have something that called arcade. And when has the sun has a different rotation, the magnetic fields has a pressure, and at some point they reconnect and poof, explode. And this cause this coronal mass ejection and explode through the solar system,
which is then seen as a storm.
Yeah.
And so the question is, this you actually answered, but wait, I have to see which one I didn't read. Yes. So do other stars also have corona? And also, can we observe it without eclipses?
No. The other stars has corona too, but we can see directly. We can see through the X-rays, but we can use only the eclipse technique in the sun, because it's the closest star, it's the near star. But in other stars, we can see the corona through the X-rays, because it's very, very energetic part of the sun.
But for example, if you wouldn't have X-rays, would you be able, for example, to use the technique that they use to find exoplanets? So where they kind of take out the star in order to see?
No, because the corona is so dim. And if we use this technique, no, it's not possible. And if you don't see X-ray emission, probably you don't have corona. It's another open question. What are the conditions that you need to satisfy to have a corona in the star? Because we don't know. We have seen stars like the sun that has hard X-ray emission, and other stars that has any emission. We don't know.
Yeah, it's many open questions. Luckily, we have
Yeah.
sun to study it first. And there's also a question related to this. Are the sunspots bigger in bigger stars? So you say that they're very powerful. So you can see them in X-ray, but are they more powerful or bigger in the stars that are bigger as well? Or this does not cover?
In fact, the sunspot and the rotation are related. And in a bigger star, you may don't have this kind of sunspot, but in the smaller star, like dwarf M-type brown star, you can have a really big sunspot, like around 25% of the solar disk or the star disk. So it's more common in the smaller star than the sun than in the biggest star than the sun.
Okay, but so also there is question, all the stars have sunspots or just sun-like stars? But I mean, I assume, as you said, we don't really know. Or is there something?
We know that the solar light star has a sunspot. A smaller star than the sun has a sunspot, but a bigger star than the sun, no, they don't have a sunspot because the magnetic field is so weak. And this is because the convection layer is so thin, or even they don't have a convection layer. And this is why they don't have a sunspot in the part of the dark stars. They have a really big convection suns, or even is fully convection star. And for that reason, the smaller star than the sun has a really big sunspot.
Okay, that's very interesting. Thank you, Francisco. There are more questions, but I will urge people to just join us in the virtual pub. So yeah, thank you again for your talk. And
Thank you.
as well. So yeah, so now please join us in the virtual pub. The link should be in the description of the YouTube. And there we will have a short break, after which we will start with the pub quiz. So get your beer and join us. Thank you.
Hi, everyone. Welcome to the virtual pub. We'll do the quiz here and there. And please, we'll be about 5 minutes before we start. I'm just going to share the screen now that lets you see the quiz link, which is on Kahoot. You can either join it on your phone or online. And we will start in 5 minutes during the quiz. So please join as soon as you can.
Sorry, what was that?
Yeah, but you're sharing this audio. Yeah. It's just Willica and someone else who's doing the quiz. You two should do the quiz. Join the quiz. Join the quiz.
On the quiz.
Need 2 more minutes, then we'll start the quiz. I think the delay today is about half a second, so that's pretty good. Okay, Tech Crew said a bit more than half a second. Between half a second and 3. One more minute to start. All right, finish changing your usernames and then we're gonna start. Because had enough on that.
wait another minute for some people to join.
Okay, Tech Crew says there's a few more people joining, so we're going to wait another 2 minutes. All right. I'll give you 5 more seconds to finish changing your names. People keep changing their names. I'm going to go with you 14 people in 10 seconds. Someone is trying to change it again. 2 people are trying to change it again. Get your name in now because we're going to start. Welcome to our Zoom Pub today. We're here in Groningen in Zoom Pub. All our tech crew is here. That's why we're all wearing our masks as we're here together, running all the tech. Okay, 14 of you are back. So we will now, there's 1 more person joining. So we'll wait 10 seconds for this 1 more person. And then we'll start at Epic October quiz. Today, I think we have 15-ish questions. We have 2 rounds from the speakers, and then we have the 3rd round that is astronomy trivia that is coming up in general. This person number 15 is joining. Hurry up. I'm not getting a yes they are, no they aren't, yes they are, no they aren't. Now we are on 30. All right, we'll start the quiz. People can join anytime, you just get less points. Remember when you're playing the quiz that there's 2 things that are important: how quickly you answer the question, and also that you get the question right. So those 2 things you should bear in mind all the time. Also, there is a small delay between what we're talking about and what's happening in the quiz. So please bear in mind that as on your phone, it might say you have 3 seconds left. You might not, because we're a little bit ahead of you as we're broadcasting on the YouTube. It's not too bad today, but please just keep taking it in mind. Don't wait till the end of the question to answer the question. All right, and here we will go, starting today's quiz. Three, two, 1, go. So the first generation of stars have no metals in a long life, little metals in a medium life, no metals in a short life, or little metals in a long life? Which of those do you think applies to the first generation of stars that we had in our universe? Answer now and answer fast. Oh, I hear tech crew is disappointed behind me. Apparently their answers are not good. Very disappointing. And there we go. The right answer is no metals and a short life. First stars had no metals, as most of the metals in the universe had to be made by stars. So you had to have stars before they were there. A lot of depression sounds behind me. So right now we have Prime Spot is in the lead, Gagarin is second, and then other people. You can see yourselves. All right, question 2. A candle stands on a table that is 3 light hours away, and it's been there for the last 24 hours. It was lit up 2 hours ago. And what do you see now when looking at that candle? It's burned completely down. It's being lit. It's burned down partially, or it's not been lit yet. So a candle was on a table 3 light hours away that was lit 2 hours ago. There's a lot of discussion happening behind me. I can't really hear it, but I hear discussion going on. Yes, it has not been lit up yet. If it's 3 light hours away, it was lit 2 hours ago, then there's still 1 hour before you'll see it being lit. Prime Spot still doing well. Friesland Boppet getting up there. Interstellar, Drent the number 1, or climbing up.
Be sure to mention your question a few times because your face is in front of the question.
Yeah, okay. I try to move my face around. If it's in front of the question, I'll keep moving it. I try to keep moving it, but I can't really see where it is. Okay, next question. How far away is the most distant galaxy that has been observed so far? 12 billion light years, 13.4 billion light years, 32 billion light years, 52 billion light years. Oh, my head is just going to stay in front of the question no matter what I do. So the question is still, how far away is the most distant galaxy that has been observed so far? Yes, 32 billion light years. Well done, most of you. We see there a prime spot at the top, Gagarin and Ganova Fofo climbing up there. When was the intergalactic hydrogen gas basically fully ionized? When the universe was 400 million years old, 1 billion years old, 13.4 billion years old, or it's still not all ionized? When was the intergalactic hydrogen gas basically fully ionized? There you go, when the universe was 1 billion years old. Not the popular choice for 400 million years old. 1 billion is a good way to go. See what that did to the scores? Some little movements at prime spot, still in the prime spot. Moving on to question 5, we're in the next topic. How long is a solar cycle? 5, 10, 11, or 22 years? How long is a solar cycle? you last people to answer, just press the button. There we go. 11 years is the right answer. In general, 11 years long. Oh, some changes right up there at the top of the scoreboard. Frizzlin Bopper is doing much better. Interstellar, Gagarin, all up there now. Prime spot not on the prime spot anymore, I guess. What is the maximum solar latitude that sunspots can have? There's a picture to show you latitude. There you go. What is the maximum solar latitude that sunspots can have? 0 degrees, 15 degrees, 25 degrees, 30 degrees. Person number 14, press your button. You can do it. There you go. So yeah, 30 degrees is the right answer. You can get sunspots moved between the equator and to plus and minus 30 degrees as time goes on through the solar cycle. So every 11 years starts off around the solar equator and then move up and down. And you can see a little movement at the top. Everything's still to play for, as always. Let's move on to question 7 of our 15 questions. What is the mean temperature in the corona? This is the solar corona, not the coronavirus. What is the mean temperature in the corona? 4,000 Kelvin, 6,000 Kelvin, 10,000 Kelvin, 1 million Kelvin. If you prefer Celsius, just add yourself 273. If you prefer Fahrenheit, just type it into Google. Yeah, 1 million Kelvin it is. Corona is extremely hot. Bit of a problem in astrophysics. Don't ask people too many questions about it. Scoreboard still looking good. Gagarin is doing well and very much creeping up on the top spot. Everything still to play for with everyone. What space mission touched the sun? Herschel, Cassini, the Parker Solar Probe, or Solar Orbiter? What space mission has touched the sun? It is the Parker Solar Probe. Again, the majority right. A lot of people want a Cassini, which went to Saturn. So unfortunately, the opposite direction. But oh, Gagarin now in first place. Things are changing around. Prime spot back on the leaderboard again. Let's see what happens as we keep moving through these questions. Next up, we get to our general knowledge round, and this is a multi-choice. What are centaurs? Small celestial bodies sharing the orbit of a larger one. Small solar system bodies orbiting the sun between the outer planets. Mythological creatures that are a mixture of a human and a horse, and a person that reached the age of 100 years. This again, not from the talks, but for your general astronomical knowledge or general knowledge in general. Tech crew are having a lot of conversation about it in the background right now. If they win, it'll be disgrace because they can't possibly get any points at this part. There we go. There's two correct answers. Are there small solar system bodies orbiting the sun between the outer planets? So between some outer planets, you get asteroids, and those are called centaur asteroids. Also, it is a mythological creature that's a mixture between a human and a horse. It's not a small celestial body sharing the orbit of a large one. We'll see in a second. Or a person that is 100 years. As you see where the scores went. Up and down a bit. Oh, new players right up there in the scoreboard. So everything, as I keep saying, is to play for, and new people are up there right at the top. And for your information, there is small celestial bodies sharing the orbit of a larger one are Trojans. You can see them highlighted in the picture. And a person, sharing the orbit of Trojans, person that's reached the age of 100 years is a Centurion. Centaurs are that mythological creature, and the green dots, which you can see, I can't see because I'm colorblind, are the ones that are Centaur asteroids in between the orbits of planets. How many bodies in our solar system have a ring system? 3, 4, 7, 9. How many bodies in our solar system have a ring system? I think people are Googling. May as well guess. 7 it is. Who knows which 7 they are? Don't think the people behind me know the 7 that they are. I can hear them laughing about it right now. But if we go look, how did that change the scores? Not a lot. And which are the 7? The 4 gas giants we all know have rings, but also 3 minor planets have ring systems. 2 of the Centaur asteroids that we just mentioned in the last question, as well as a dwarf planet also has a ring system. Could also consider the Earth having a ring system, but it's an artificial ring in the geostationary orbit of satellites that we launched and put there. So it's not really a ring system, just one ring of geostationary satellites. Ceres is located in the Oort cloud, Batman belt, Van Allen belt, or asteroid belt. Where is Ceres? Yes, the asteroid belt. Well done, almost everyone. Whoever thinks the Batman belt, good job. Maybe tech crew think that, I don't know. Little bit of movement in the leaderboard. 2 more questions to go. Everything still to play for, even in that top ranking, everything is still to play for. Everything is possible. Oh, now it's going to tell you about it. Sorry, I forgot. There you are. Ceres is in the asteroid belt. It's big. So finally, the total mass of the asteroid belt is roughly equal to what? A 3% of that of the moon, 50% of that of the moon, a third of that of Mars, or the same of the Earth. So finally, the total mass of the asteroid belt is roughly equal to what? 3% of the moon, 50% of the moon, a third of Mars, or that of Earth. So if I add all the asteroids together, how much mass do I get? And the answer is 3% of the moon. So let's see how things have gone. With the podium, Frizzlin' Bopper in 3rd place, Rose in 2nd place, and in 1st place, Gagarin. So if you are a winner, please screenshot your phone and send it to us. And we will give you options of what the prize may be. There's various options and prizes depending on what and when can happen in going out in the coronavirus time. And right now we recommend that everyone come join us in the Zoom pub. If you're not already there, come to the Zoom pub at http://stem.oo/Zoom pub, and you can join us right there. If it gives you a security warning, just press advance and say go anyway. We don't know why that's happening right now, but you're as safe as going anywhere else online. So please come join us there. And thank you for joining us tonight. Thank you for being in the quiz. Happy World Space Week to everyone. And we look forward to seeing you in our Zoom pub in a few seconds time. So please come over there and meet us all. And you can meet these tech crew guys behind me who are having hysterical laughter about everything that I say. Thanks for joining. See you next time. Come to the pub. If you didn't hear the link, it's in the description below in the YouTube if you're watching on YouTube.